Good morning. Welcome to the video lecture on design of RCC elements. Today we are going to see about the demonstrate design of flexure for flanged beams. So far we have seen about the beams, that is singly reinforced and doubly reinforced, of rectangular section alone. Today we are going for different geometry, that is called as flanged beams. Flanged beams, what is meant by flanged? The beam is having a flange along with its web. Okay. Normally in rectangular section we have only the web part. We don't have any flange part because we have a depth full depth as D alone for your beam. Okay, right. Flanged beams, we can call it as L beams and T beams. That is, in the shape of L and in the shape of T, we can call the beams as flanged beams. Okay. Why we need flanged beams? Usually in conventional beam columns slab system, we'll go for a slab, in between we have a beams system. So that in order to reduce my depth of the beam in a floor deck, I can go for T-beam system. That is, the web portion will act as a rectangular part and the top portion, it will be monolithically constructed with my slab. This is my slab, then this is my beam. This top portion of my beam, it is fully covered with concrete. It will take care of my compressive stresses, whereas the bottom portion below my neutral axis will take care of my tension stresses. That's why I am been giving more amount of breadth to my top flange. That is, to take care of my compression, I am been taking the slab itself as a compression member to my beam. That is called as monolithic construction. During construction, the slab steel should follow in the same manner as it is. The beam main reinforcement will be there in your slabs. This is called as monolithic construction. This I can call it as T-beam. Okay. What is meant by L-beam? When the floor deck system is proceeding, at the end we have a slab. This is the end of my slab. Here will provide a beam, right? This is called as L-beam. Usually it is we can see as inverted L-beam. Okay, right. Coming to now flanged beams, we have T-beam and we have L-beam. I have drawn a picture for my T-beam first. This is my breadth of the flange, whereas the rectangular beam will have a same breadth at the top and the bottom. That is, above your neutral axis, the compression is taken care by the concrete, the tension is taken care by the steel. As of now, the compression will be taken care lightly by the concrete. You can reduce the depth also. You can enlarge your breadth. So that's why we are following BF, that is the enlargement of my breadth, and DF, this is my depth of my flange, or else the depth of my slab, or slab depth. Whatever slab depth you have provided, you can take it as DF for my beam also. Then till the tensile reinforcement where it is, you can take as effective depth D. Then DW is my depth of the web portion alone. BW is my breadth of my web portion. Okay. In a normal conventional beam column slab system, this is the slab it has been following. It is for, say, for ground floor. This is the slab, or first floor, or anything else. This is the slab. Normally we have a beam system. At this end we can call it as L beam. In between we have so many beams. This beam you can call it as T beam. This T beam and L beam is also called it as flanged beams. The beams having flanges within it is called as flanged beams. Okay. We have certain conditions related to IS 456 code, how to take up the breadth of the flange, how to calculate the breadth of the flange. Then how to calculate the depth of the flange. Then how to keep your BW, that is breadth of your web and depth of your. We have certain criterias. Then we need to satisfy our codal requirements also. Our code says for breadth of the flange BF, the slab should be monolithic with beam. The slab part should be monolithically constructed with my beam part. That is, the steel should be prolonged into the beam breadth flange also. Then the main reinforcement in the slab should be parallel to my beam. This is the main reinforcement provided in a slab. This should be parallel. This is the T-beam in between your slabs. This main reinforcement should be parallel to my beam. Third one, providing transverse reinforcement in the slab should not be less than 60% of the main reinforcement at the midspan. At the midspan, it will undergo some deflection, so that you need to provide above 60% of the main reinforcement what you have provided parallel to my beam. Okay. Then how to calculate the B effective value? B effective value is nothing but L0 divided by 6 plus 6 times of DF, that is your depth of the flange or your slab thickness, plus BW. B effective is equal to BW plus half of center to center of beam on either sides of your supporting condition. In either case you can take, here L0 is nothing but the distance between the points of zero moments in your beam, that is the L0 value. Okay, if it is an isolated beam, you can go for B effective as L0 divided by L0 by B plus 4 plus BW. You can take in this value also. This is what you need to calculate the B effective value. It is not directly known by us because it is not a rectangular beam. Okay, then the thickness of the flange. Thickness of the flange, that is D effective, we can take it as the slab depth what you are providing for slab directly. Then another one, you may ask why we need to take the depth of the slab as depth of the flange, because this is purely based on the bending in transverse direction. The slab will bend in the same way it will be bent along with your beam because it is monolithically constructed. That's why it is purely based on bending in transverse direction. Okay, then we'll see the next criteria. The next criteria is breadth of the web. Breadth of the web is nothing but breadth of the beam in tensile zone. It is not in the compressive zone. It is mainly purely based on the tensile zone width. Why we need to take care of my tensile zone? Because it has been monolithically constructed, it should have sufficient lateral stability, or else it will be rotating. So it should be sufficient to provide lateral stability to your structure, the entire floor deck system. That's why we are providing enough breadth to take care of my stability. Or else we can take as width of the column also. If the column width here, we can provide column, this column width as usual as beam breadth, then or else 1/3 the height of the web. This is my height of the web, or I can take it as 1/3 the height of the web also. Okay, then how to take the depth of the web? DW. DW, this is my total small d, that is my effective depth, is equal to DW plus DF. This is my DW, this is my DF. If we know already, you can directly take the small d. Then how to calculate the depth when it is simply supported condition? This is simply supported. When my beam is simply supported, I can take 1/12 to 1/15 of my span, that is my L value, or else if it is a continuous beam, 1/15 to 1/20 of the span. Then if it is continuous, this is for light loads. Then it is for medium loads, I can take 1/12 to 1/15 of my span. Then for heavier loads of continuous beam, I can take 1/10 of 1/12 of the span. Because most of all, when it is a flanged beam, we'll go for continuous beam systems. That's why for light loads, for medium loads and heavy loads, we can take all these cases. Mostly we'll go for heavier load conditions. For many cases, we'll take 1/10 to 1/12 of my span. This is what we need to take the dimension requirements for my T-beam system. We'll see for L-beam system, it is almost same as T-beam system, but only one thing differing is it is at the edge, right? The beam is at the edge. When the beam is capturing the load, it may be W, you may have some eccentric load from your center line of your beam. Some eccentricity you may have because the load can't be transferred directly along the center line of your beam. That's why it will make some eccentricity in your beam, because in the T-beam system it is been directly following along the center line. The load carried by a slab is directly transferring everything to the center line, so that the axis will take everything, so you don't get any eccentricity. But here this load you may have some eccentricity E. Having eccentricity in this beam, what happen is that you will have a load W, then this eccentric load will cause a moment M. This is the moment due to which the beam will have a rotational capacity, that is, then due to this load and moment it may cause some torque. Torque is nothing but torsion. This beam may induce torsion. All the edge beams may induce torsion. So you need to take care while designing the edge beams, you need to take care the eccentric load and also for the torsion. Okay, the codal requirements for this L beam is that to calculate the BF value, L0 by 12 plus BW plus 3 times the DF. For isolated beam, BF is equal to 0.5 L0 divided by L0 by B plus 4 into BW. These are the conditions we need to take to calculate my breadth of my flange. Okay, if it is for continuous beams and frames, I need to take L0 as 0.7 times L. It is enough. L0 here also same, the distance between the points of zero moments in my beam. As of now, we all know about the requirements of the cross section needed for my L beam and T beam. Now we will see about the stress block parameters. Stress block parameters. This is my D beam. I will be providing the reinforcement. This is my D. This is my neutral axis line. Point 002 proof strain, 0.0035, this is the ultimate strain. Till how? This is T. Till then it is vertical, will have a parabolic fashion. This is Cu, as same in my limit state design stress strain blocks. This is my DF. This is 0.45 FCK. This is 0.42 XU. This TU is equal to 0.87 FY into AST. Under equilibrium condition, Cu you can equate to Tu. We can write Cu as 0.36 FCK BF into XU. There we'll write only the B. Here the compression part is taken care by the flange. That's why we are been writing. This is the BF value. Here we are taking BF, that is into XU is equal to 0.87 FY into AST. The same way XU by D is equal to 0.87 FY AST divided by 0.36 FCK BF into D. Then here when XU is less than DF, we can treat as rectangular section. When your XU is less than DF, that is the neutral axis lies inside the flange, rectangular section. When XU is greater than DF, you can treat neutral axis fall outside the flange, compression of web to be taken. Okay, the compression of web to be taken part. Okay, the limiting moment of resistance dF divided by d should not be not greater than 0.2. This is the condition for this flanged beams. We will see the limiting moment of resistance value. The same part mu is equal to 0.36 XU max. This is the limiting moment of resistance for the rectangular section into 1 minus 0.42 XU max by d into FCK BW d square plus 0.45 FCK BF minus BW into DF into D minus DF divided by 2. These are the formula to calculate the moment of resistance for limiting section. Okay, when dF by d is less than it is greater than 0.2, we can write mu is equal to 0.36 XU max by d 1 minus 0.42 XU max by d into FCK BW d square plus 0.45 FCK BF minus BW into YF into D minus YF divided by 2. When it is greater than 0.2, I need to take the flange, the depth of the flange, that is the centroidal value of the flange. Here you can take the depth of the flange, that is below the neutral axis, that is the depth of the YF value. Okay, then how to calculate YF? YF is equal to 0.15 XU plus 0.65 DF. It should not greater than, condition is that it should not be greater than the DF, that is the depth of the flange value. YF should not be greater than the depth of the flange value. Okay, then when XU max is greater than XU, that is when XU is greater than DF, I can go for the neutral axis fall outside the flange. When the condition is like that, I will go for this. Then DF divided by XU, which is greater than 0.43, DF value, the depth of the flange, divided by XU, which is not greater than 0.43 value, I can adopt the same conditions of DF divided by D not greater than 0.2, that is this value, the first value. Then when DF by XU is greater than 0.43, I can go for DF by D, which is greater than 2. This condition will be adopted as same like this condition. This condition will be adopted as this condition persists. Or else if everything is going beyond the XU max, you need to check the XU value, then you need to check with XU max value. When it exceeds both, you can write it as under over reinforced section, or you need to redesign the section for doubly reinforced section also. If not, it will be in singly reinforced section. We will see one problem related to T-beam. Problem 1. Design of T-beam. Effective span given as 8 meter. Simply supported. Spacing of beam 3.3 meter center to center. Thickness of slab given it as 130 mm. Width of web is 300 mm, total depth 450 mm, live load on floor is 10 kilonewton per meter square, floor finish is 0.75 kilonewton per meter square, beam supports partition wall, load 12 kilonewton per meter run, adopt M20 and FE 4 and 5. These are the conditions. I'll draw quickly the diagrammatic representation of my problem. This is my 130 mm depth of my slab. This is my 300 mm. This is my 450 mm. The center to center distance of another beam is 3.3 meter. I'll quickly go through step 1, load calculation. Weight of slab 25 into 0.13, 3.25 kilonewton per meter square. Weight of finishes 0.75 kilonewton per meter. Live load 10 kilonewton per meter. Total load is that 14 kilonewton per meter. Then load on beam from slab. What is the load on beam from slab? This is 14 into 3.3. That is the distance between the next support. That is 46.2 kilonewton per meter. From wall. From wall, how much amount of load? That is 12 kilonewton per meter. That is the given. Then weight of a rib. That is the beam. 0.3 into 0.45, that is the effective depth, minus of 0.13. This is the weight of the rib into 25. This is the bottom portion of my beam. That is 2.4 kilonewton per meter. So on the whole, the total load, this is what the slab and the finishes and the live load. I can calculate the total load. Then load from my beam to this beam from the slab, that is 14. This is the load from the slab into 3.3, that is the distance between from the wall. Then the weight of the rib, I need to calculate the total again. Again the total load is 60.6 kilonewton meter. Now coming to the picture, what is WU? That is 1.5 times 60.6, I will get 90.9 kilonewton per meter. We all know MUD is equal to WL squared. It is the simply supported condition. So I will get 727.2 kilonewton meter. Now I will calculate BF value, that is L0 by 6 plus BW plus 6 times DF. I will get 2.413 meter. This L0 I need to take the value as 8. 8 is given. The effective span is given. So BW we know 0.3. Then DF we know 0.13. I will get this value. So from this the effective depth may be 450 minus 80, that is equal to 330 mm. Okay. I will go for step 2. Here we need to assume whether the XU lies inside the flange or outside the flange. First, I will assume that XU is equal to DF. So, I will calculate MU1 as 0.36 FCK, BF, DF, D minus 0.42 DF. I will get around 623.18 into 10 power 6 Newton meter, where mu d I have calculated, which is greater than mu1, so neutral axis falls outside the flange value. Then second assumption, assume df by xu is equal to 0.43, that is equal to 303.3 mm. So Cu, that is the web portion, 0.36 FCK XU into BW, that is equal to 655 kilonewton force. Then YF I can calculate from this as 0.15 XU plus 0.65 DF is equal to 130 mm, which is less than or equal to my depth of the flange. Now I can calculate the CUF value as 0.45 FCK BF minus BW into YF. I'll get around 245 kilonewton. Now I can able to calculate, this is the compressive force required, this is the for web portion and the flange portion. Now I can calculate the ultimate moment for web is that CUW into D minus 0.42 XU, that is the force into the lever arm distance. For this I will get around 133 kilonewton meter. Mu2 is equal to MUW plus MUF. I'll take MUF is equal to CUF into D minus 0.5 DF, that is equal to 649.31 kilonewton meter. So I'll get MU2 as 782.84 kilonewton meter, whereas MUD value, which is less than MU2. So I'll go for trial and error. XU is less than 7/3 of DF. So I'll go for trial 1 value. XU is less than 7/3 DF, which is less than 303.3 mm. Which is less than the 303 value. So I will assume XU as 230 mm. I need to check whether the same procedure will follow, whether my XU lies over here or where I will get my exact moment. So XU I will put it as 230 mm. For this XU the same procedure is repeating. Again I need to calculate YF. The YF value is 119 mm. Mu is nothing but 723 kilonewton mm. Then I will go for trial 2. I will put XU is equal to 235 mm. I will get YF as 119.75. So I will get Mu as 727.57 kilonewton meter. Now it is almost equal to my MUD. MUD what I got is 727, which is, this is greater. When I give this value, it is being lesser. When I put XU as 235 mm, it will be almost equal to MUD value. Hence I can follow this XU is equal to 235 mm. So for this 235 mm, again I need to proceed this MCW, MCF and MU2, the same procedure. From this I need to calculate my AST value. Okay, I will calculate CU, the force for my web, 0.36 FCK XU BW, 507 kilonewton. CUF, that is equal to 0.45 FCK BF minus BW into YF is equal to 225 kilonewton. Cu, adding the both, I will get 276.5 kilonewton, that is CUW plus CUF. This is my force exerted. Then I need to calculate the AST now. AST is equal to Cu divided by 0.87 Fy, that is equal to 276 into 10 power 3 divided by 0.87 into 4 and 5. I'll get around AST as 7657 mm square. For this I can provide any 25 mm die of bars of so many numbers. This is the procedure. First thing, we need to calculate the load calculations. From the load, after getting WU, you need to calculate MU. MU, you need some BF value. After calculating BF value, you need to locate the XU, where it has been located. It is the XU, the neutral axis depth, whether it located in the flange or below the flange. For that, you need to go for more trials. If it is okay, your bending moment satisfy all these criteria, you can take the AST value. Now we'll see another problem. Quickly, problem 2. It has been for doubly reinforced section. T-beam, BF is equal to 750 mm, B is equal to 250 mm, D is equal to 500 mm, then DF is equal to 90 mm, M it is given 300 kilonewton meter. I have take MU as 1.5 times 300 as 450 kilonewton meter. Step 1. First step, you need to arrive XU is equal to, it is equal to your depth of the flange. For that you will get MU1 value 224 kilonewton meter. Here this is MUD, this MUD it is greater than MU1, so NA will lie outside the flange. So trial, I'll go for trial. If it is inside, I'll don't go for trial. I'll keep the same reinforcement. Okay. Trial 1, XU is equal to 7/3 of DF, that is equal to 210 mm. So I'll calculate MU2, that is equal to 338 kilonewton meter, which is less than MUD. So I'll go for the next trial. Trial 2. XU greater than 7/3 DF greater than 210 mm. Now XU is equal to XU max, I can put, that is 0.48 into 500. I'll get around 239.5 mm. So the DF by D is equal to 0.18, which is less than 0.2. When the DF by D is less than 0.2, I can go with the formula of DF, the formula which is having DF. I'll go with MU limit. The conditions of DF divided by D less than 0.2 formula. For MU limit, I have got as 355 kilonewton meter, which is less than MUD, that is my limiting. Here, when MUD is greater than the MU limit, this is the limiting value, but our conditions MUD is greater, so I'll go for obviously doubly reinforced. If not, I'll be proceeding with singly reinforced section. Okay, now I know that it is a doubly reinforced section, so I'll provide AST1 for MU limit. ASW is equal to 0.36 FCK XU max BW divided by 0.87 Fy. I'll get around 1194 mm square. Then for flange value, that is 0.45 FCK. This is my web portion, this is for my flange portion. BF minus, I'll be neglecting my web value into DF divided by 0.87 Fy. Here I am neglecting the web. here only the web alone. Here I need to take the flange alone. So 1112 mm square. So the both the AST1 is equal to, add these two values, I'll get around 2306 mm square. So B, additional tensile area steel is AST2. We know the D dash is 50 mm, it is given in the problem. So AST2 is equal to the MUD, which has been greater, minus MU limit. MU limit is smaller, so I need to neglect. This is the additional steel I need to provide in my section. So 0.87 Fy into D minus D dash. I'll get around 583 mm square. So third one, compression steel area ASC. So AST2, I need to calculate the second one, AST2. So for that ASC, I know the formula MUD minus MU limit divided by FSC, that is for your compression, that is FSC. For the tension it is 0.87 Fy. FSC minus 0.45 FCK value into D minus D dash. Then for this FSC I need to calculate epsilon SC 0.0035 into XU max minus D dash divided by XU max. So I'll get around 0.00275, or else I'll get around this value. For this value FSC is equal to 351.8 Newton per mm square. This is from code book. So I'll get AST as AST2 as 614 Newton per mm square. Total AST is equal to AST1 plus AST2, that is around 2889 mm square. This is what we need to check, whether the XU, whether the MUD is greater, we need to go for doubly reinforced, or else we to go for singly reinforced section. These are the procedures to calculate or to design my moment and AST for a flanged beam section. The T-beam also same as L-beam, only the difference is we need to calculate the breadth of the flange. That formula is alone differ, except that it is almost same. Okay, thank you.